Welcome back. We are going to finish off this chapter by talking about the reactions of epoxides, what they do. So, the first thing is to a quick review on how we can synthesize epoxides. The main way is from alkenes and using our proxy group. So, start off, we have, say, alkene, and we use MCPBA, which is monochloroperoxybenzoic acid, plus MCPBA. But not mono, but metachloro. Meta is the 1,3 position. Benzoic acid, peroxybenzoic acid. And what's that going to do? You consume my oxidizing portion and form our epoxide. And it just comes metachlorobenzoic acid. That so it's essentially a concerted mechanism. I'm not going to redraw it, but essentially that the ring, the pi cloud of the ring of the double bond donates into the oxygen, and a lone pair of the oxygen donates into the one of the carbons, and you have a complete rearrangement of all the bonds within the benzoic acid, peroxybenzoic acid, to reform a benzoic acid. But that is just one easy way to do that. Another way is there's another proxy group, magnesium monoperoxo phthalate. So magnesium, you'll see some similarities here. Minus and two of those groups stabilized by magnesium. The previous one was halogen soluble. This one is water soluble. So MMPP. It'd be magnesium monoperoxo phthalate. But it does the same thing. We can also occasionally see a base promoted cyclization of a halohydrin. It's another way we can form this. So remember what a halohydrin is. Our alcohol group adjacent to the halogen group, and then use some base deprotonates that. The lone pair goes here. So the next step, we have our alkoxy group right next to a really convenient leaving group. So lone pair swings down, attacks the next, and kicks off our leaving group. So that's another way we form epoxides. Like chlorohydrin plus sodium hydroxide would form a epoxide. We can also cyclize tetrahydrofuran and tetrahydropuran with a bulky base. So as another example, those are not quite true epoxides, but they're that. So like we can have say like this group is, so this is going to draw this guy out, chloro, put a functional group just so we can see some of this. But okay, so 1, 2, 3, 4, 5. So that'd be right there. That is be, it's like 5 chloro, 2 2 pentanol. It's a halohydrin, but in the presence of a bulky base like 2,6-lutadiene. So what is this bulky base? 2,6-lutadiene. It's a not quite a benzyl group, but it's a 6-membered nitrogen-containing cyclized group, and the base here is this nitrogen. There's 2,6 in the presence of 2,6-lutadiene. Lutadiene. Same thing. We attack here, and then this is going to eventually attack over there and cyclize that. So we're going to form. Oh, that's. There'd be what? 1-methyl tetrahydrofuran. Now, those are just a couple ways we can make epoxides, but epoxides aren't really made to last. They are particularly very reactive in the presence of many different things. So some of the reactions we can see is acid catalyzed ring openings. In the presence of, say, an acid. So let's draw a presence of an acid. Essentially, what's happening? The lone pair is going to attack there, pronate this. Then we have from there a good leaving group. But the thing of it is, it's only good leaving group from one side. It's not going to leave both sides at the same time. So if it's symmetrical here, we could attack from either side. But now we have, in the presence of water, we can either attack here and kick that up, or attack there and kick that up. Either way, you attack there, swings up, swinging arm. So we have an alcohol, and now we have a pronated alcohol. And in the presence of more water, you just depronate it to regenerate our base. Sorry, not, oh, for God's sake. Regenerate our acid. So we get a mix of enantiomers. Because the way you got to think about this is a backside attack. If this is epoxides are both going to be syn in order for this to work. So they either all going to be up from the ring or down from the ring. And so when that water comes in, it attacks from the back, wherever that epoxide is. So you have one alcohol going up and one alcohol going down. So you would either have there or like there, regardless. So if you did a alcohol instead of water, you're going to get a hydroxy ether. So just depending on what group you add here, on that step is going to depend on what our ending product looks like. If I use a hydrohalic acid, so HCl, HBr, HI, we're going to get a halohydride. And if you have enough of the acid, you're going to get a dihalide, which not always super useful. So But the whole idea is that acid first makes the epoxide unstable, capable of being a good leaving group, and something comes in and replaces it, whether it's water or an alcohol or allergen. It all depends. That's working from the acidic standpoint. We could also have a base catalyzed epoxide ring open. Now, this is a lower activation energy than the ether attack, but it's similar to the acidic, but it needs harsher conditions. So if I was going to make like the so uh, in the case of same ring, we'll go ahead and use a different ring. It's fine. Basically, in presence of a base, base comes in attacks somewhere, swing up, and we have our, oh no, we have our alkoxide group and our base minus. We have a pronated base, depronates it, and now we have our ring opened. Now, depending on order and what we do, depends on what we're going to get. So just looking at this, okay. You can do this a completely different way and get different results. So depending on whether you want to go acid catalyzed or base catalyzed. So you got to think about what we're doing. So this is 1,2 let's say 1,1 dimethyl oxirane. If I go about this the acid catalyzed route, 1, I pronate, and then 2, I add an ether, an alcohol, dimethyl ether. So pronate that. The oxygen on there is going to go to the place that can better handle the guy that can better handle the charge is going to lose the oxygen. So in this case, we have we have unsymmetry. Asymmetry. So as this is pronated, we get a choice of which one is the better, which guy is the better attack point. Is it going to be this guy or the guy on the left or the guy on the right, the carbon on the left or the carbon on the right? Which guy can better handle a positive charge? Is it the primary carbocation or the tertiary carbocation? Well, if you remember, tertiary carbocations are more stable than primary carbocations. So which ways is going to attack? And step 2, the alcohol is going to be attacking there because the oxygen is having to donate more electron density, the epoxy donate more electron density into the primary carbon. So it's going to swing up. And so after it's all said and done, what do we have? You have the ether there and the alcohol there. If I go about it from the other way, step 1 is I use, say, a ethoxy group, and step 2, I use then just ethanol. You're going to get the other product because when we attack, O minus before here, we're going to attack maybe the less sterically hindered, the more less sterically hindered position. Right now, this can essentially do a two-step. This can swing open to make a carbocation to stabilize this. This epoxide is rather stable, and so what we have is we end up first attacking here. So which one of these guys can better stabilize? Plus, which one of these guys can better stabilize the O minus? Well, gonna have right here. So when all is said and done, if we do it the other way around, they scalized, we're gonna have an alcohol there and the ether there. So we got to think about how we're going to do this. Acid catalyzed, essentially, this oxygen can ring open the essentially be ring open to stabilize itself and make the carbocation. Which one be the more stable carbocation? The tertiary. And the O minus, which one has more electron density, is going to be the one that's less likely to be attacked. The tertiary carbon has a lot more electron density in there. So from the two adjacent carbons, the other one doesn't have, so it's going to attack the primary. So it's less sterically hindered there. So, in acid, we pronate the OH and then put a much larger partial charge on the more substituted carbon, yeah. So in the base, it's just an SN2. So it's really the least hindered carbon. So we're looking at SN2 versus kind of more of a SN1. Real quick, Grignard. You can do Grignard with epoxides. And that's where we're going to finish up. Quick reminder of Grignard reagent. Grignard reagent is a very acidic addition of our group. So in the presence here, arm. Step 1, in the presence of ether. We have RMGX or even RLI, organolithium. And step 2, we use acid. Essentially, we're attacking kind of the base catalyzed mechanism, because R minus is just acting as a base. So R minus is going to go attack to the least sterically hindered, and we're going to have our O minus R, and then the acid protonates that. So we have our alcohol group. So Grignard attacks the least substituted. It's very similar to the base catalyzed. So acid catalyzed, it's kind of like SN1. Base catalyzed, it's essentially an SN2 reaction that's least substituted. And so the same thing with Grignard. It's very similar to base catalyzed. Why? Because Grignard is essentially making a Lewis base, a stabilized Lewis base that is capable of attacking any acidic position. So that is where we're stopping. Thank you for your time. This is the end of chapter 14, ethers, thioethers, and epoxides.